without being like without intervention from anybody. Because of that, what happens? I might lose the information again. So that is the crosstalk error. And there is one more error is I intend to read the information of the quantum qubit, but I make a mistakes in reading out the information because of the measurement operators which I prepare in the first place. Okay, so measurement operators which I prepare, I might not, I might, okay, okay, so I might lose the information which I am measuring, okay, which I wanted, but I measure something else. Because of that, what happens? Because of that, what happens? I might end up in the wrong calculation once again. Okay, fine. So that is the error coming from measurement operators as it is. And there is one more error comes from the system is a T1, T2 relaxation. So T1, T2 relaxations are, okay. So what I mean by T1, T2 relaxation, when I prepare a system and trying to create a superposition state, what happens when I'm preparing the superposition state? What happens? The qubit or the electron supposed to exist at the excited state for some time. That is the excitation lifetime. What is that excitation lifetime? Some lifetime it will have. Okay. So what is that lifetime? Right? So let's say for any given electron to get excited to some level, okay, excited to some level, the lifetime is 1 microsecond. But within that microsecond, what happens? Things comes down to ground state. So because of T1 time, which is supposed to be 1 microsecond, which is less than 1 microsecond happens, due to that, I might create a superposition in a wrong form more than what is required. Okay. So that is a T1 error. And there is also called a T2 relaxation. T2 relaxation in the sense, superposition state supposed to exist for some time, that is a T2 time, but due to the problem in the system, T2 gets relaxed, means T2 gets reduced to smaller number. Again, the superposition is not there for me to do the full-fledged calculation which I meant in the first place. Okay. So there is a control line noise error. Control line noise error, which is, okay, the signal fluctuation. I have a signal which is supposed to go and talk to a qubit and transfer the information and retrieve the information by another signal, but there is a control signal fluctuation within that may also cause errors in the calculation. Okay. As usual, the thermal noise is always there, which comes from the surrounding, so which is shown also here at the right. Okay. And the most important thing is I prepare a quantum state initially in zero form, means a classical 0 bit I'll prepare, and later on what happens, it goes to evolve into the required superposition when I send a Hadamard gate action onto that, and so on. But the initial preparation itself is a problem. It's like a raw material has some problem in the raw material, then also I may end up in the wrong calculations. Okay, right? So these are the most important forms of errors comes into the quantum communication. Okay, so anyone has any doubt or anything, please unmute yourself and ask me. I would be very happy to repeat if needed. Okay, right? Okay, so I'm not looking at any chat messages. So since it's a Google Meet, you can unmute yourself and ask me if there is anything to be asked. Fine. So these are the quantum sources of noises which we will have in our quantum communication. Okay. Now this slide slightly explains. Okay, let me enlarge. Yeah. So types of quantum errors. Earlier I just showed you what are the sources of quantum errors. Now because of those sources, what happens and what kind of errors would happen is showed in this slide. Okay, here if you see, okay, I think I can go for a presentation mode, full screen mode, right? Yeah, right. So here if you just see, there is something called a bit flip error. Bit flip in the sense, the 0 becoming 1 means 0 gets rotated from z axis to minus z axis. Okay, it is a big problem for us. 0 becoming 1, 1 becoming 0 is a big issue. So that's a bit flip error in our quantum computing. Okay, and one more is, let's say quantum state is projected along the x direction. Okay, x direction in the sense 0 ket plus 1 ket divided by square root of 2. Along the x direction it is pointed out, quantum superposition state. Because of the problem in the system, because of the error, let's say instead of pointing towards the positive x-axis, it gets rotated to the negative x-axis. What I mean is, instead of 0 ket plus 1 ket, it becomes 0 minus 1 ket. That is what the minus ket actually showed here in the second figure. So on the top I showed you a bit flip error from positive z axis to negative z axis, quantum state getting rotated about. In the second case, phase flip means quantum gate projecting towards the positive x-axis gets flipped to negative x-axis. In that way, what happens? There is an error comes into the picture. Okay, and there is one more error is called a depolarization error. Depolarization error means I choose a collection of certain qubits. Among those qubits, some of them are going out of the superposition state which I want, and they may create some kind of a mixed system instead of pure quantum system. So the moment the system becomes mixed, I will represent that quantum state using density matrices, because the quantum state representation is not going to be sufficient there. So the system becomes so much mixed. Okay, because of the mixedness, I would usually term the system as depolarized system, or depolarization is taking place. So it is another domain, another zone of error. As of now, we will not touch how to correct that particular error. Only way to correct that error, let me tell you, you can simply disregard those unpolarized quantum states and only keep with the polarized, or means the states which gone out of control. You just eliminate them and use the ones which we have in the control. Only that is the solution for us. Means you only take some part of the mixed system which is pure in the first place and use it for the computation. Okay, right? So that is the one of the direct default correction there. But most importantly, the errors happens because of the bit flip. Errors happens because of the phase flip. How do you address them? That is what we are going to see in the today's session. Okay, right? So we just saw what are the sources of the error, what kind of errors may takes place in the computation. We just saw. Okay, very good. Now let me open some window. Yeah, very good. Now let me go to see how the classical computing people are doing the error correction. Okay, and we'll just see how these people are doing by looking at the classical error correction, and we'll see, is there any possibility to just take a page from their method and come up with our own method, so that we will have a correction, bit flip and phase flip correction in our case. Okay, right now let's see what is the classical errors. As usual, if I intend to store information as a 0, it is not going to remain 0, it is going to get flipped to 1. Okay, right? So now I use a mathematical method called Markovian method. Here I'll just give in terms of probabilities. Let's say 0 gets flipped to 1 with a probability 3 and remains intact as 0 with a probability of -1 - 3. Okay, right? So, if somebody is having unmuted, please, Jignaji, please mute yourself. Yeah, Madam, Parvatam, Madam, please. Yeah, thank you. Okay, right. So, 0 becoming 1 with a probability P and remaining intact with 1 minus P. Let's say if I take any bit in a classical communication, it is remains to be 0 with the same 1 minus P probability, but it is shifting with the probability. If that is the case, okay, if that is the case, what I will do, I'll just try to address them in terms of probabilities. Very good. Now, what is the case of 1 when I intend to store 1 bit? If it is not remaining as a 1 bit, okay, it flips to 0 bit. Let's say I'll call it as 0 becoming 1, 1 becoming 0 in a given vicinity and neighborhood of a computation in a circuit, which means both of them should be of equal probability of flipping. So what I'll do, 1 becoming 0, okay, I will say with a probability P it will happen. With 1 minus P probability, it is not going to happen of flipping. Okay, very good. So I will have this kind of a probability transition of 0 to 1, 1 to 0. I have it here. Now, this is what the classical computing people are going to represent their bit flips. Okay, right? Now it's actually called a binary symmetric channel. Fine. Now they are going to address this by something called creating a logical 0 bit and logical 1 bit. What is that? I'll tell you. If there is a 0 bit, they know in the first place, as the 0 bit goes through some error gate or a problematic gate, it becomes 1, and 1 goes through error gate, it becomes 0. Okay, and the gate error only happens on one single bit. Let's say if that is the situation, in that case what they will do, they will take a 0 bit and replicate or clone into 3 0 bits and take 1 bit, clone into 3 1 bits, and they will call the 3 zeros as a logical 0. They will call triple 1 as a logical 1. The understanding or the agreement here is, we know that if there are 3 bits going through the error problematic gate, okay, only one of the bit among them gets affected, because the ability of this gate, error gate, is to create error only on the single bit. By majority, what you will do, if you 3 bits going through the classical gate, only one of them is flipped, the other 2 are there to tell that the actual signal is the 0 bit because of the majority. Similar story you can apply for 1 bit and 1 logical bit also. There, if the 3 ones going through the classical gate, one of them getting flipped means, very good. If one of them is flipping, the other 2 guys are there to tell us, or tell at the outside, this is in fact a 1 bit, because as per the majority, there are 2 ones, 1 0. Okay. Remember, this kind of a strategy only works when I have more than, okay, when I have more number of bits to tell me by majority what is the actual signal. So here in this particular case, we know in advance there is only 1 bit is going to be flipped. That's why what we did, we added 2 more bits to that bit and we sent as a logical 0. So if there is a chance of only 1 bit being flipped, means I have to create a logical bit with a 3 individual bits. Remember that. So only single bit is going to be compromised, means I have to prepare a logical bit of 3 bits. Okay, same story for 1 bit also. Now, okay, let's say there are 2 bits are going to be flipped. In that case, what we should do, we have to take a 5 bits of logical bit. Okay, 5 bits of logical bit. By doing it, what happens? If the 2 bits are going to be compromised, the other 3 are there to tell by majority. Okay, the actual signal is 0, the actual signal is 1, depending on as it goes through the quantum classical error gates. Okay, right? So this is the logic they were using for a classical error correction. Now, here I have what is this limitations of majority voting error correction to work here is, okay, let's say uh, the P is the probability with this something is flipping. Okay, if two bits are going to be flipped and remaining bit is not remaining one bit remains intact, in that case what happens, I might completely go into the wrong conclusion. Okay, so for the mathematics statistics, here I have given what is the chance of two bits getting flipped, one bit remaining intact. Among the three bits, this is the equation, which is 3p square 1 multiplied by 1 minus p plus p cube. And probability of error here, if you just simplify this expression, which is comes out to be 3p square minus 2 into p cube. Okay, fine, that is there. Now, if you just say if the probability of any single bit flipping is less than half a percent, fine, no problem. Overall error is under control. If P is greater than half, which means the two bits are going to be flipped without my intervention, okay, with more than 50% of error, in that case I will be in a serious trouble, because probability of error is going to be more than 50%. So more than 50% error means we can't get rid of that, or we can't have a ability to go ahead with a confidence for the computation. So that is what the mathematics here. So remember one thing, if there is only one bit is going to be flipped, that means I have to prepare a logical bit with the three bits. If there is two bits are going to be flipped, I have to prepare a logical with the five qubits or 5 bits. I'm sorry, a quantum bit is coming in between. We'll come to quantum bit as we go further. Okay. Now, okay, so classical computing people are doing very good. They're doing with this logical technique. Now, am I allowed to do the same kind of a strategy or use that same strategy in the case of quantum computing? Okay, the answer for that particular question is straight away no. Why no? Because okay, there is no cloning in the quantum computing, right? So classical people can clone any bit into any bit, any number of bits. It's just like a fan out operation. Electronics people would know that I have a signal going with some voltage. I can connect it parallelly, get the same voltage. Okay, just tapping the information out. So in that way, I can tap as much as I want. The intensity of the information get reduced. I use some amplifiers. Okay, but the cloning where whatever is possible in the classical computing is absolutely not possible in quantum computing. What I mean is, let's say I have a qubit of superposition. That superposition I can't replicate several number of times. One thing I can do, I can destroy a superposition from somewhere and create the same kind of a superposition somewhere. It's like conservation of quantum states. One place I destroy, I create at one more place. So it is the same state preparing somewhere else. It is a quantum teleportation for you, but you are never able to go and create a multiple copies of a quantum qubit. So this is the one of the main obstruction or a hurdle for quantum error correction, because the entire logic of creating a logical bit there in a classical computing relies on cloning a bit into multiple bits. Okay, fine. Okay, keep it aside. As we going through, we have a first hurdle. Now, the next hurdle for us is in the classical computing. Let's say there is a place, there is a circuit, there is a gate somewhere. It is a problematic gate, and we will address that gate by some logical bit error correction strategy. Okay, then we are done with that. We can go ahead with a calculation. But when it comes to quantum computing, it is not that straightforward. Why? Because the errors are going to happen very, very continuously. Continuously in the sense, okay, like at some place I am going to create a correction. Okay, I was doing a correction there, some correction or doing some error correction. Immediately at some other point, some other error is going to creep in. I'll go there and I'll try to create error correction there. Again, it is. So the errors are happening, continuously happening errors. So at one point you are doing to correct, another point it comes. So it's a infinite number of resources are possible, infinite number of errors are possible. So you need to have a serious precision in doing error correction. So that is the one more problem in classical quantum computing. Okay, and one more hurdle, the third hurdle for you is, okay, here, let's say I want to know there is an error in the signal. What I should do? I have to do a measurement. But the problem for the measurement in quantum communication is the moment you measure something, what happens? It gets destroyed. All the measurements are actually going to destroy the quantumness or disturb the quantum state from one form to other form. So you can't do the measurement. Without doing measurement, how can you find the signal? How can you find there is error or not? So altogether, these three things are just putting a just deadlock for going ahead for a quantum error correction. Okay, right? So no cloning, errors are continuous, measurement destroys the quantum information. Okay, right? So people thought, how I am going to tackle all these three things and go ahead with the error correction. Okay, right? So sometimes when one door shuts, people say there is other door gets open up. Okay, so in that way, if you just see, right, there is a way to tackle these things. There is a way to convert the disadvantage into the advantage. Okay, right? So what we can do is, let's take a page from a classical computing people itself. What I will do now, I am not going for a cloning. Okay, let's say for the time being, I ensure that system is perfectly isolated. It only talks to the signal which I send. Okay, in that way, I'll just ensure that errors are not continuous. Errors are happening here and there. Okay, so the second hurdle is being removed. The third hurdle is I'll use a very, very advanced readout technique, okay, where the information is not going to be destroyed, superposition information is not going to be destroyed, it will be kept intact. What for that, what I'll do, I'll have a test qubit or a probe qubit. I'll have, it is called a readout qubit. So that readout qubit I bring near to the signal qubit and just extract the information without disturbing its without state. Okay, that is possible, by the way, right? Okay, so if I do that, the third hurdle is also going to be eliminated to a certain extent. Okay, now what is the first one? The most important one is I can't clone a superposition state to multiple superposition state. Very good, let it be. What I will do now, I will use something called a logical qubit is being created. How do I create a logical qubit? Let's say I have a qubit I0 A0 ket plus B1 ket. Let's say I have. Okay, fine. I have this. Now, what I will do, see, this is a one bit. Instead of sending this information on one bit, what I will do, I will not replicate this one superposition to three superpositions. What I will do, I will take the three qubits. Okay, I'll put the information of A and B on the three qubits. Okay, just to see the difference. Okay, I'll just give a simple real world classical example. What example I'm going to give is, let's say I have a big box, very large box. Okay, right? So if I send it by one person, such box, this a large box is there. Okay, so I want to send the information of that large box to some third party. Okay, right? I know that the one person carrying that box, he may fell down somewhere, he may destroy the box, so information get destroyed. So what I will do classically, I will ask three persons of the three persons, I'll ask them to carry each such boxes and go to the destination. Okay, what I'm doing there, I am just ensuring if one person fell down, other two people are going, and then tell other people are going and carrying the same such boxes and telling the third party that this is the boxes which is supposed to be sent in the first place. As per the majority, the third person will take and assess it. Okay, fine. Even this person who has fell down and broken, if he brings the wrong information, he will think that this is not a right information, it's a wrong information, and he will just ignore that guy. So this is what classical computing people are doing, creating a superposition state, sorry, creating a logical bit with multiple bits. Such a thing is not possible here. So what I will do, I will, instead of sending that large box by one person, what I will do, I'll ask the three people, just please come over here. You all three together carry this entire box and go to that third party. So by doing it, what I'm ensuring, let's say among the three people, if the one guy just falls down, other two are there to carry that strongly. So that is the logic here in the quantum computing. Just to take the analogy which I gave into the real world imagination, and then just think that that is what the quantum error correction is all about. Okay. So here you see three qubits, both are, all the three can exist in superposition state with the probability amplitudes A and B. Okay, there I am calling all the three zero bits as a logical zero bit ket, and all the three one bits are all the three one ket. I'm calling it as a logical ket one. Okay, now what I'm doing, I'm creating a superposition of logical kets. Okay, superposition of basis states which are actually encoded into the new logical 0L and 01, sorry, 1L. Okay, fine. And what is the difference here? Earlier, my superposition was defined on a computational basis of 0 and 1. It is just a 2-qubit system, and the basis is just 0 and 1. Now, my information actually lying on 3-qubit system. What is a 3-qubit system? 3-qubit system has how many basis elements? 8 basis elements. Among them, I only chosen 2 basis elements, 000, 111. These 2 basis elements I am chosen, and I use those 2 basis elements, create a superposition, and I am sending this information through that superposition. Remember, there are other 6 elements are there here in the basis of 3 qubits. Those were unused. Okay, what are those things? If I want, I can list it down here: 001, 010, 100, okay, 011, 101, 110. So these are the another 6 basis elements of 3-qubit system which are not being used here. Okay, right? So if I do it now, you can just imagine the 3 qubits are carrying along the way. If the one of the guy got distracted or he has fell down because of the problem in the path, the other 2 guys are there to carry that information. So that is the quantum error correction for you. Now, this is just for the sake of saying theory. Now, when it comes to the experiments, how I am going to do, this kind of a encoding, how I am going to do this kind of a conversion from single bit superposition to 3-bit superposition of this kind of a transition. How I am going to do? Very good. Let me show you the circuit. Okay. So this is a circuit for you, right? You have a superposition state which I am supposed to send, and I will have a 0 and syllabus. I take one more 0 and syllabus. What I'll do, I use a C0 gate from my actual quantum register to the ancilla registers. So quantum state is a control, ancilla state is a target. Okay, if you use such as quantum gate encoding or circuit encoding, what you get at the output, if you see carefully, whenever control is 0, target remains 0. Whenever is control 1, target gets flipped. Okay, because of that, I am getting a superposition state of 0, 0, 0 and 1, 1, 1. Okay, so I have used A and B here. In the next case, I am using alpha and beta. Please don't mind that. Alpha and beta, I meant A and B. Okay, right? So this is how I am going to convert or encode the information into these qubits with the same superposition. See, the information is same. What is the information here? Alpha, beta. What is the information here? Alpha, beta. Only difference is one qubit is carrying the same information. Here, 3 bits together carrying the information. Most important thing. 3 bits carrying the information. Okay. Now, among these 3 bits, which guy got a problem? Okay, we need to find out which guy has an issue. Which guy has an issue? He just got flipped. Is 0 becoming 1? Is 1 becoming 0? If it happens, how do I find? That's the question. So, how do I do a detection? Error detection, or in scientific term, I have to diagnose a syndrome, or I can say a syndrome diagnosis I have to do. For that, is there a way? Okay. Yes, there is a way. What is that way is, I am going to create a testing tools. Okay, just like a person is having some kind of a fever or not. Okay, I have a thermometer which tells me, by bringing the thermometer into the vicinity of the person, I would know the person is having a temperature by seeing how the mercury in the thermometer get enlarged, means expand. From there, I just calibrate and find out how much expansion corresponding to the heat emitted by a person. In that way, I'll figure out a person is having some problem, health temperature. Okay. Likewise, there are 3 qubits here. Which qubit got affected? I want to find out. Now, what I'll do? Let's say a person is having a fever. For that, I have a tool. Let's say a person is having some blood pressure issue, high BP or low BP. For that, I have a blood pressure monitor to find the temperature. I have some other issue, like say some person is having some other issue. As a doctor, I will have another tool to measure that. Okay, all the way. Let's say no qubit is flipped, so I need to have one tool which tells me, if the tool goes near to the 3 qubits and tells me, of course, there are no errors. Okay, there is one tool which goes near to the qubit and tests which qubit got flipped. Only one qubit got flipped. Which one it is? So for that, I need to have a toolkit. And let's say there is a tool which tells me, it goes near to the 3 qubits and tells me there are 2 qubits going to be flipped or got flipped. Which are those two? It should tell me. Okay, there is a one probe which tells me all the 3 qubits, sorry, all the 2 qubits, the 3 qubits got flipped. Okay, right? So likewise, I have a tool which is unique. You see, I create the tools out of the basis elements itself. What is the basis elements? The basis elements for me, which is the 8 qubit, sorry, 3 qubit basis elements, which are all zeros, all ones, one of them one, two of them is one, all the three of them is one. That is the basis elements. Okay, so here I am going to create something called a projection operator, which is just like a tool which is going to help me in figuring out given qubits are compromised or not. So I will have a projection operator P naught, which is a matrix created out of two of the basis elements by taking a outer product. Okay, so 0, 0, 0 outer product with 0, 0, 0 plus 111 outer product with 111, it is going to give me a 8 by 8 matrix. Okay, and what is this? Tell me, when I take this projection operator acted upon the resulting quantum state. Okay, if I have a quantum state superposition created with the logical zeros and logical ones, if it is gone through some circuit, if after the coming out from the circuit, if that has some trouble, if that has some problem, this projection operator P naught is going to tell me that is actually flipped or not. Okay, so it is going to tell me it is actually flipped or not. How do you take? How do you know? Take the P naught, act on the given quantum state which is coming out from the circuit. Okay, right? So let's say I have a quantum state psi. You do a P naught operation, right? If you are finding a measurement operator means a projection operator action on a quantum state means you are not going to only multiply from the left side, you also has to do a multiplication on the right side also. When you do the multiplication on the right side, what happens? Psi P naught psi, if it is going to give you a 0 means you can think that none of the qubits in your system are actually flipped, they remained intact. Why? Because you see, there is a 000, there is a 111 ket in the quantum state, and my projection operator is having 000 and 111. So there is a inner products are going to give me 1. Okay, so none of the inner product is going to give me 0. So I'll get the measurement of P naught with a quantum state psi is 1, which is I can just like say convince myself none of the qubits are actually flipped, so I can just go ahead and do the calculation. So that's what I mean. If the projection operator P naught is used and I'll get a 1, means I can say no error. So P naught is a projection operator which helps me to find there is a no error in the system. Okay, right? So I'll just finish all these three P1, P2, P3 description, and we'll quickly take a 5 minutes break before, after that, and then we'll come back. Okay. Now there is a other projection operator I will create out of. I'll create out of two basis elements. What are the two basis elements? 100 and 011 basis elements I'll take. What I mean by that is, let's say one of the bit is being compromised. Which one? Let's say the first one is being compromised. In that case, I'll create a projection operator with the first one being compromised. Suppose all the zeros has to be 0, but first one got flipped. All the bits has to be in a one superposition, 111, but first one got compromised. You see? Okay? Right? If the first one got compromised here in this superposition, what happens? 0 becomes 1, 1 becoming 0. To find that, I'll create a projection operator P1 with using them itself. Okay? So outer product of 100 with itself, outer product of 011 with itself, together gives me a matrix which is going to tell me if in action of P1 on a given quantum state is 1, you can straight away say there is a bit flip happening in the quantum circuit. Where it is happening? In the first qubit case it is happening. Okay? Similar story you can apply for, let's say second qubit is going to be flipped, that is recognized or detected by projection operator P2 and projection operator P3 when it happens in the third qubit. See, the projection operators I have constructed out of the basis elements itself. Okay, so just by action of P0, P1, P2, P3 on a given quantum state, without disturbing its quantumness, I am able to find what is happening in the transition. Okay, right? So this is how I am going to find which qubit in my logical qubit is going to be compromised. Okay, whether it is a first one or a second one or third one, Once I figure it out, I can come up with some error correction code, or so now I have done the detection. In the later stage, I will do something called a recovery of that particular bit back to the normalcy. That we will see after this 5 minutes break. Okay, so let's have a 5 minutes break. If somebody has some doubt, you can ask me. I would be happy to answer.
Hello, good morning, sir. Can you hear me?
Yeah, I can hear you, sir.
Yes, sir. Sir, last class I have seen that you have done some unitary matrix while adding function and all. That unitary matrix we have to design, sir, depending upon the function, sir.
Very good question, sir. Absolutely beautiful question. Okay, right. Yeah, see, sir, unitary matrix means, okay, let me see, I can write something. Okay, sir, you can mute yourself. There is a background noise from your end.
Okay, sir. I'll mute, sir.
Ah, okay, so I'm going to use my Google Keep Notes. Okay, right. Okay, sir. Question you asked is beautiful question, sir. Okay, that's very important. Everybody should know actually what it is. So the unitary matrix U, okay, is equal to exponential of minus I. H is a Hamiltonian. I'll just put a hat over that. T divided by Planck's constant H cut. So this is a unitary matrix, sir. So what is this unitary matrix? It is going to act on any quantum state psi, converts that quantum state into some new quantum state psi prime. Okay. The example would be, let me reduce that. The example would be a X gate acting on a superposition state, giving me a new superposition state where alpha betas are interchanged. Okay, right? So that is a unitary gate. X gate is a unitary gate. Now the question you asked, will come back to that. Now unitary gate is a X gate. Now what is a H corresponding to that? Okay, what is this H corresponding to that? We should know. Now the answer to your question is, for every gate operation. For every gate operation, how are you going to realize that gate operation? Let's say, right? Let's say I have a quantum states. Let's say there is a 0 bit, there is a 1 bit. Let's say there is an electron in the ground state. Okay, I want to put that to excite state. I want to send it to excited state. What I will do? I will send a photon of having energy exactly equal to the separation between these two levels. So that photon is having some h omega, okay, which matches with this energy separation between 0 and 1. What happens? The electron which is in 0 goes to 1. Single photon having energy which is equivalent to 0 to 1 separation pushes the quantum state from 0 to 1. That is a kind of a X gate operation for you. Now, for this X gate, what is the corresponding Hamiltonian? Okay, so what is the corresponding Hamiltonian? Because I know on the left hand side I have a X. Okay, let me write down that equation. On the left hand side I have a X gate operation, which is exponential minus I h divided by h cut. Okay, now X gate, I know what is the X gate for, right? If you want, I can just write down X gate form, which is 0 1 1 0. This is X gate form. Now I know the left hand side. For on the right hand side, I have a Hamiltonian. So you can find out in a reverse manner what is the corresponding Hamiltonian for a given X gate. I'll put a subscript X for that. Okay. So The X gate Hamiltonian means what for you? Hamiltonian is in a classical notation analogy, Hamiltonian which describes total energy of the system. So Hamiltonian usually in a classical manner, let me write down, Hamiltonian H is kinetic energy plus potential energy. That is what the Hamiltonian usually is. So kinetic energy is half mv square. Potential energy is depending on the system. Let's say a system is, let's say I have a mobile which is placed on the table. So the height of the table gives you some potential energy to this mobile. The same story, if the system is put in a certain potential, let's say electron is surrounded by so many other charges, so it is inside that potential. So I'll have some potential expression. U, not confused with the U used for unitary. So potential energy is some function of time and space. Okay, right? So in a classical world, you can think it as some kind of a potential energy acquired with all altitude. When it comes to quantum computing or a quantum physics, the system is being surrounded by every other charges. That is a potential energy. How much energy it is actually existing in what control it is existing in, that is captured in a potential energy. Okay. Now, this is the classical analogy of a Hamiltonian. When it comes to a quantum computing, the Hamiltonian is actually represented by Schrodinger equation expression, where Hamiltonian is going to take minus h square by 2m gradient square for the kinetic energy plus u operator potential energy. Okay, so this is the Hamiltonian corresponding to any given system surrounding or the neighborhood. Now I have here in the unitary operator, on the left hand side I have a matrix, on the right hand side I am supposed to have a matrix, remember. So that means the Hamiltonian will also be a matrix. Okay, so for a X gate there exists an Hamiltonian in the form of matrix. Okay, how do I just how do I know? There is an expression I have written here. You are saying a matrix, so there may be confusion. Of course not. I can write the system in description as a total energy, kinetic energy plus potential energy of the system, or also I can capture this information in the form of matrix. What is that? So I have used the matrix to represent about the system. In the same way, the X gate I represented in terms of matrix. In the same way, I can represent the Hamiltonian in terms of matrix. So, for every unitary gate, X gate or a Y gate or a Z gate or a H gate or the C naught gate or anything you take, there exists a Hamiltonian corresponding to that gate. So that Hamiltonian you can find in a reverse fashion. What is that? You can just take a log of this entire matrix. Okay, I'll show you what is that. For a corresponding to X gate, what is the Hamiltonian? I'll show you. You just take a log of X. On the left hand side, what you will have? On the left hand side, you have minus IH cut Hamiltonian, sorry, I T divided by H cut. Now, send everything to the right. The Hamiltonian is going to be, okay, right? I by I into H cross, okay, I into H cross log of X divided by T. This is your Hamiltonian. Okay, so for a corresponding every gate there is a Hamiltonian. You can simply now generalize H Hamiltonian for any gate. So above one I have written, for X gate I have written, for any gate the Hamiltonian would be IH cross log of the unitary gate divided by time. What time? It's up to you. Okay, so this is the Hamiltonian corresponding to any unitary gate, whether it's a X gate, a Y gate, or a Z gate. Just replace U with that corresponding gate. Okay, So the answer to your question is straightforward. You need to prepare yourself the corresponding unitary gate by setting up the Hamiltonian or by creating a situation. Okay, how do I create a situation? How do I create a superposition state from a ground state of a qubit? Okay, I have a qubit strictly in the ground. I will send a superposition. I'll send something called pi by 2 pulse. The area of the pulse is pi by 2, which is in fact what it is consisting of. It consisting of equally spaced time span wise equally spaced photons. What are they? There is a first photon which comes and puts the electron in the excited state. The electron stays there for 1 microsecond. It can't stay there for 1 microsecond. After for 1 microsecond, it comes back down. By the time it is coming down, I'll just exactly space another photon 1 microsecond apart. Okay, so that photon will push the electron again back to the excited state. Okay, by the time it comes down, another photon I'll send. So the sequence of photons are actually consisted in this pi by 2 pulse. Okay, so in that way what happens, the electron does the hopping between ground and excited. That is what the superposition for you. So on paper, what is the gate which does that? H gate, the Hadamard gate, the Hadamard gate, okay, which does the superposition, which puts the system in superposition by acting on the zero cache. So the equivalence, experimental equivalence for that is sending a pi by 2 pulse to the quantum ground state qubit. Okay, so sending a pi by 2 pulse is captured in the Hamiltonian. You see now, sending a pi by 2 is pi by 2 pulse energy you are supplying. So how much energy you are supplying? You have to write a matrix. That matrix is a Hamiltonian matrix. Using that matrix, you can create a unitary matrix, which is supposed to be a Hadamard gate. Okay, so just to avoid the confusion between so many Hadamard, so many things, actually is represented for Hamiltonian and Hadamard gate. So just to avoid the confusion, I'll just put a HD stands for Hadamard gate, or even people use a W for the Hadamard gate in the name of Welsh gate. Okay, right? So remember, you need to create a situation of quantum gate operation. So you are creating some energy transition where the system's energy going to change. That energy change is actually captured in the Hamiltonian. So how the system is changing is represented by the unitary operator. Okay, am I able to answer your question, Yogi ji?
Yes, sir.
Okay,
Thank you,
so
sir.
please remember one thing. Okay, for example, let's say, so there is a student. Okay, he's a very weak student. Okay, I want to raise his level. What I should do? I have to train him. I have to give him extra exercises. I want to help him. So I'm creating a situation of adding extra knowledge to him. The extra knowledge adding is a process. Added knowledge and everything I represent as a Hamiltonian. Okay, the process of adding all these things, change of the nature of the person is actually represented by this process. Okay, fine. Yeah.
Yes, sir. Thank you, sir.
Okay. 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 I hope others also have for other have followed. Okay, so I'll take a 2 minutes break, I guess, myself. Uh, in fact, it's a very good exercise. Okay, none of the books talks about. Okay, For every gate operation, there is a Hamiltonian associated with it. Okay, right? Whether you can start from X gate, Y gate, or Z gate, okay, or even Hadamard gate or C naught gate, any gate operation, okay, we know the gate operations by matrices, right? So what is the corresponding Hamiltonian for these gates? If you can find out and note down, it will be very, very satisfying exercise. Okay, right? So for X gate, what is the Hadamard gate? For Y gate, what is the corresponding Hadamard gate? Okay, the experimentalists will know. They will just only send some signal, some laser pulses. Okay, for them, that is the Hadamard gate operation, that is the X gate operation, that is the Y gate operation, Z gate operation for them. Okay, but as a theoretician or as a teacher, okay, you want to convey this idea to the student. It's a very good exercise. Okay, right. Okay, so we have another 40 minutes. So let me start. Okay. Hmm. Let's to just to reconnect where we are at. And okay, here if you see so far, what did we discuss is we discussed about the errors in quantum computing, where they're coming from, sources of errors. Okay, what kind of errors? How classical computing people are doing error correction? Okay, and can we do that? If we can do that, what would be the limitation? Okay, so straight away, the implementing that error strategy, error correction strategy, is not possible. Okay, why it's not possible? There are three hurdles, very basic errors, the hurdles. Okay, so those hurdles, how I am going to address them? Okay, right? So yeah, just a minute. Okay, so one is no cloning, another one is errors are continuous. Okay, other one is measurements destroys the quantum operations or quantum state. So without disturbing it, we have to do that. Okay, that is can be taken care. And errors, continuous errors can be taken care by ensuring system is nicely isolated. Okay, those things are possible. But one thing is absolutely not possible is no cloning. I can't do the cloning. Okay, I can't do the cloning. So how do I do? How do I bypass and do that? Is a technique called encoding. How do I encode? Instead of sending information on one bit, I send the information on 3 qubits. Same information, not replicated information. Okay, there is a circuit for us. Very good. Using that, two C naughts, two ancilla qubits. See, the ones with are the zero are the ancilla, like a scapegoats. They got sacrificed. We prepare a new superposition state with the same information. Okay. Now that encoded information is sent through calculation or a quantum circuit. After the circuit operation, we wanted to know, have we done any change? Have we done any problem? Any circuit has created any issue? For that, we have projection operators where P naught would tell me acting on a quantum state. If I get probability P naught action on quantum state is equal to 1, which means I know no errors are occurred. P1 action on side gives 1 means 1 got flipped. Which one? The first one. Okay. So if you act a P1 or a P1, P2, P3, only one of them is going to give you 1. Remember, that is the only situation we considered here. We have not considered a situation where 2 bits are going to be flipped. Okay. In that case, we have to have one more strategy. Okay. Right now, we are confining to the case of only 1 bit is going to be compromised. In that case, this strategy works. Okay, right? So now we need to do the recovery. What is the recovery is, let's say no bit is being compromised or no errors are there. You just do nothing. Okay. What I mean is P naught of action on psi gives you 1 means no need to go and measure P1, P2, P3. So you can keep quiet. You can say, oh, like our system has no errors. Okay. But if P1 giving you a measurement on psi, giving you 1 means there is a first bit is being compromised, first bit is flipped. Okay, for that we need to do the recovery. What is that recovery? We need to reflip back the first qubit back to original, flip the first qubit again. Okay, let's say the P2 gives you 1 measurement on quantum state, means the second bit is flipped. We need to flip back the second qubit again. Same story for the third qubit. Remember, only one of them is going to give you 1. So accordingly, I will reflip back that particular qubit. Okay, all right. Remember, if the P of flipping any one is less than half, fine, no issue. Okay, if P of flipping one of them is more than half, I can do this correction. If P of the flipping of more than 1 qubit is being flipped with more than 50%, then I'm in trouble. That situation I'm not considering here. I'm only considering a situation only 1 bit is being flipped with a probability either half or less than half. Okay, right? So the recovery, now there is error analysis here. You can read through. Okay, you can skip this one. If time permits, we'll come back to here. Okay, now how do I do the error correction? Okay, let me see whether do I have that. Yes, where is that? Okay, 1 minute. Okay, phase flip error diagnosis. Okay, yeah, looks like it is not there, that equation. What I will do, I will use my hand notes and explain again. Okay, right? So let me exit the presentation here. So that will come. Okay, presentation. Yeah. Okay. So okay. Right. I hope we can see. Right. Let me take a different color. Maybe a black color. Okay. Right. Now we have a quantum state. Okay. We have a quantum state which is alpha 0 0 0 plus beta 1 1 1 1. This is the encoded state. Okay, and this state supposed to travel, okay, and go through some gate operation and come back intact. But the problem is it is not coming intact. It is going to be changed. Let's say it is gone through some unitary gate operation and it got compromised into psi prime. What is the compromise? The compromise is the first qubit got flipped. Okay, you see now, first bit, instead of being 0, it become 1. Instead of being 1, it becoming 0. Okay, right? So this is what the compromise it is being happened. Now, as you can see, you take this new quantum state, you act on P0, okay, you are going to get 0 there because there is an error occurred. You know why? There is error occurred. But P naught is what? P naught actually made up of, P naught is made up of outer product of zeros, outer product of ones. Okay. So when you take this measurement on P naught, on the psi prime, you see, you are going to get 0. Means there is error occurred, so the P naught is going to not give 1. Which one gives you 1? P1 gives you 1. P1 going to give you 1. Okay. This is going to be 1. Why? Because you know what is P1 by the way? P1 is 100 outer with 100 plus, okay, 011 outer 011. Okay, so this is the projection operator for you here. So this projection operator, you see, so already psi has 100 in it, and this P1 projection operator has 100. Okay, psi prime has 011, this projection operator has 011. So obviously you are going to get 1. If you want, I can show you P1 acting on psi prime is, okay, 00100 plus 011 011. This entire thing, okay, acting on alpha 100 plus beta 011. Now there are two terms which are going to be multiplied onto this. Okay, let's say the first term, the inner product between 100 to 100 is 1. Okay, right? So what I'll get? Alpha into 100 of this term. Okay, right? And now inner product of 011 with 011 is 1. So these two gives me one term with a beta, this 011. Okay. Now P1 acting on the psi prime is this quantity. Now P1 acted also on the left side psi prime. By the way, this is the psi prime. On the left hand side also you act a psi prime. You are going to get an inner product of psi prime with the psi prime itself, which is 1. Okay. So P1 is giving you 1 means the first bit is being compromised. For that, what should I do? I have to recover. I have to get it back. I have a psi prime. Okay. I have to get back the psi. What should I do? First bit I have to reflip back or flip again. So for that, what I will do? For the first bit I will act X gate. For a second bit I do nothing, identity gate. For a third bit also I do nothing, identity gate. Okay. So basically what I will have, I'll have a recovery. I have a recovery gate operation. UR is looks like X tensor I tensor I. So this is a recovery gate. So what is this recovery gate does? It is going to act on psi prime. Okay. What is the psi prime by the way? Psi prime is alpha 0, remain just a minute, alpha 0, sorry, alpha 100 plus beta 011. Whenever X goes and acts on the first qubit, I goes and act on 0, I goes act on 0. Nothing happens to the 00 because it's identity gate, but X gate acting on 0 gives me 000. X gate acting on 1 gives you 1, 1, 1, 1. So I got a recovered quantum state. Okay. So this is how you are going to do the recovery. What is that recovery gate? Recovery gate is a sequence of X with I. Okay. Now this is how the recovery is going to be done. Now remember one thing, which is to be recovered. depending on whether the measurement P1 is giving you 1, okay, or not. Okay, if measurement P1 is giving you 1, so I should add the UR1. Okay, what is the UR1? This is a UR1. Okay, so if the second one is, if the second qubit is going to be flipped, means the second qubit flipped means the quantum state P2 is gives you 1, which means my recovery qubit would be, so recovery gate would be UR2 would be, okay, see carefully, nothing is on first qubit, X gate on the second qubit, identity on the last qubit. This is the recovery quantum gate operation for you. In the case of second bit is going to be compromised. Okay, if the third qubit is compromised, in that case, I'll have identity on the first and second, and third is X gate. Okay, so this is how I am going to have a recovery by knowing whether E naught is giving you 1, don't do nothing, no doing anything. Okay, if P1 is giving you 1, means you have to act a unitary recovery. If P2 is 1, you have to act UR2. Okay, right? If P3 is 1, you have to act UR3. Okay, so this is how recovery is being done. Now the question is, if you see carefully here, I have to make a measurements of, let's say, error is there, first measurement will tell me, and one of them is measured. Okay, so I have to make a measurement of P1, P2, and P3. All the three I have to make. Okay, so there are 4 measurements I have to make. So people thought, can we find out, instead of doing a 4 measurement, can we do it in just a 2 measurements? Right? So in that way I can reduce the computation time. So that is possible. What is that is? What is that is? Let's say a quantum state is alpha 000 plus beta 11. What we can do is, let's say I act as Z1 gate on the first qubit, Z2 gate on the first qubit. Okay, you see, this is the technique. And the third, on the third qubit, I'll act as identity gate. If you act the quantum gates like this, what is happening now? Okay, if you carefully see, Z1 acts on the first, Z2 gate acts on the second. Okay, right? So which means I'll have, okay, identity on the third. Identity does nothing to remember. So what I have a result here is alpha 000 plus, now the same set would go and act on the second part also. Okay, so Z1 acting on 1 gives you minus sign, Z2 acting on 1 qubit gives you another minus sign. One minus is already coming from the first qubit, another minus coming from the second qubit, so it becomes a plus. So identity acting on 1 gives you 1 itself. So any that qubits are same. Okay, so which implies first and, okay, first and second qubit are, okay, qubits are same. Okay, now this is telling me first and second qubits are same. Now what you can do, one more thing. What is that? Identity Z1, Z2 act on, sorry, Z2 and Z3. I'm sorry. Okay, identity. Okay, let me write down neatly once again. Identity, identity Z1, Z2 and Z3. If you act on this on a quantum state, okay, right, on a quantum state, type sign. If it gives you the same quantum state means I can say 2 and 3 are same. If I acquire a minus sign means 2 and 3 are different means one of them is having a issue. So I can show you that case even now. Let's say third qubit got flipped. Okay. So what is the third qubit got flipped? The quantum state would look like 001 with alpha plus beta 110. This is third bit flip na. So now you act this the top correction, the top measurement on the this. What happens? You see Z2 acting on 0, Z2 acting on 0, you see 0, Z3 acting on 1 gives you 1, minus 1, not just 1, minus 1. Okay, right? Now identity acting on 1 keeps you 1 as it is. Z2 acting on 1 gives you a minus sign. Okay, let me put that minus sign here. Okay, and Z3 acting on 0 keeps you 0 as it is. So now there is a minus sign here, there is a minus sign for alpha and beta. What you do, take the common. Okay, take the common. You just take the common. So what it means? The quantum state giving you minus sign when I act this measurement. Okay, which measurement? I Z2 Z3 measurement. If I do on the quantum state, I'm getting a minus sign means I would know the third qubit is being compromised. Okay, so just with the two measurements I can find out which is actually compromised. So let me show you that. Okay, right. Yeah, see here, if Z1 Z2 along with I acting on that gives you a plus sign, Z2 Z3 in the starting there is I plus 1 gives you means no error has occurred. If Z2 Z3 acting gives you a positive sign means first two qubits are same. Okay, if Z2 Z3 giving minus 1 means the last two qubits are errored. One of them is errored. Which one is errored? First two are same, second two are different means third one is errored. So I need to act a X3 gate on that. So in this way, what I will be doing? I will see two measurements I will do, Z1, Z2 and Z2, Z3 measurements I will do on the quantum state. I will see which one is giving minus sign. Let's say both of the measurements are giving minus sign, minus 1, minus means here I can conclude the first two qubits are different, second two qubits are different, which means, okay, first two are different, second two are different means possibly the mid guy is maybe different because there is only one qubit is flipped in our situation here, which means Z2 or the Q2 is being compromised. So I need to do a error correction with the X2 on that particular one. Okay. So instead of making four measurements of P0, P1, P2, P3, what I'll do? I'll just do a only two measurements. Z1, Z2 measurements and Z2, Z3 measurements together. If I'll do and I'll figure it out what to do as an error correction. Okay, that is a theory for you. When it comes to quantum circuit, this is the circuit it should look like for you. Okay. Now, if you carefully see, you forget about the top. In the bottom, if you see, I have written, okay, first I will encode the quantum system to the given quantum system into a 3-qubit system. Okay, right? So there is a small correction here. This is the ancilla. Okay, ancilla zeros. So I will be getting instead of one qubit carrying the same information, 3 qubit carrying the information after the encoding. Now On those 3 qubits, carefully if you see, on the 3 qubits, what I have, I'll make a Z1, Z2 and identity operation on the 3 qubits. Okay. Whatever operations I'll make, I'll be getting some result. Based on the result, I will do the correction of X gate operation on the corresponding qubit, and Z2 Z3 operation also I will make a correct measurement I'll make depending on the result, whether I'll get a positive or a negative sign as per our table here. Okay, I'll take that information and act whether x1, x2, x3 I will decide. Now who will decide? I will use some logical if statement. If this is so, you act something here. Okay. Now there is a technique of phase kickback is being used here. That is why you see usually control not means control, depending on the control target getting manipulated here. See here control is at the bottom, target is at the top. Now the information is in the passing in reverse fashion. How? From the target, information is going in the reverse fashion from top to bottom and then into the recovery. Okay, logical, through the logical control logic. Now, how it is possible? Because for any C naught, if you put a Hadamard's on the either side of a control, information travels in the reverse fashion. I have a discussion for you here. Let me show you. Yeah, here you see. Okay. Usually, see, this is a control Z gate. So depending on the control, the target gets changed as per the Z operation. Instead of that, what I will do, if you add two Haramard gates at the control, now what happens? Information flows in a reverse fashion. It just becomes like a control NOT gate from the bottom to top. Okay, so this kind of a equivalence actually exists in the case of quantum circuits. So information usually travels from control to target gate. The moment you add a Hadamard's either side of the control, it becomes a reverse fashion. In that case, okay, instead of having a control Z gate, we'll have, okay, control X gate from the bottom to the top. Here, control Z gate from top to bottom becomes control X gate from the bottom to the top. Okay, so that strategy which is being followed here. Wait a minute. Yeah. Okay. Right. So instead of having controlled Z from bottom to the top, what we are having? Controlled NOT operation from top to the bottom. Okay, the information flows from top to the bottom. Now, whatever is the information here, a logical if condition, and if something is so, do something. What is that? Do something. Act x1, x2, and x3. Who will tell? Some logical control will tell to act on that. So in this way, recovery is done. Once the recovery is done, you can get back to the actual signal by reversing the ancilla. Okay, ancilla circuit or encoding circuit becomes a decoding circuit if you reverse the same again. So you get back to quantum state again. So in this way, quantum error correction is being done for a 3-qubit flip code error method. Okay, right? Now, let's say I have a phase flip. Okay, phase flip in the sense there is a plus gate becoming a minus gate. That is a phase flip. Okay. Now, what I will do, in addition to encoding 2 C naughts, I will add 3 Hadamard gates. The moment you do that Hadamard, what is happening? What is happening is, instead of having an information carried on just 1 qubit in plus gate and minus gate, it is carried on logical zeros in the form of 3 pluses and 3 minuses. Okay, the moment you do, you know if one of them is compromised from plus to minus, you can do the measurement using the projection operator. You see, only difference from previous projection operators to this projection operators is only I have in place of zeros I have pluses, in place of minuses I have in place of zeros ones I have minuses. Okay, so just like projection operator P0, P1, P2, P3, here I have P0 prime, P1 prime, P2 prime, and P3 prime. Okay, so I will make a measurement of P0 prime, P1 prime, and P2 prime, and P3 prime on the output quantum state and find out whether the compromise happened of phase flip on the first qubit or a second qubit or a third qubit. Okay, so the strategy would be same. Okay, right? What is the strategy? Strategy is just like whatever we did. First, we encode. From the encoded information, we find out which location there is a compromise. Based on that, you get the recovery back. Okay, right? Let me show you. This is a 9-qubit code, error code. Ah, I think I have full circuit somewhere. Okay, 1 minute. This is encoding. Somewhere here I have. Yeah, I think this is a circuit. Okay, so this is a phase flip error correction code. After this, you will do the recovery by reversing the same thing at the right side. Okay, right? So if I have to do, let's say the error is happening in more than few qubits, in that case, we'll go for sure 9-qubit error correction code. Even up to 4 qubits gets compromised. Even in that case, there are 5 more majority qubits are there. They will tell me what was the problem. Okay, right? So how to encode? The same thing. Every qubit is like flipped, like created to 3 more qubit. Here you see, this is what we will be doing. Okay, and so this is what 9-qubit error correction code would look like. You can see a part of it is a 3-qubit code, so it is repeated 3 times, means 9-qubit code for you. Okay, so it's discussed as a humming bound. So if you want, you can go through. There is a hand notes description is given. Everything is written in detail. You can read through and understand. Okay. So I'll just stop at this point. If there are any questions, we'll just address those questions. Okay. Right. Yeah. If people have any questions, please unmute yourself and ask. Or if you are hesitating, you can do send a message on the chat. I'm just seeing the chat messages also.
Participants, participants, any doubts, please ask.
Even any doubts from my first 2 topics? Okay. And okay, so we did discuss something on Wednesday and Thursday. And Wednesday, first day, I did do introduction to quantum computing. And day Thursday, I did discuss about introduction to quantum algorithms. Started with quantum parallelism, and I discussed Dutch algorithm in very much detail. If you have anything to be asked, even in those 2 days topics, you are welcome to ask. Okay. Not only that, you can ask me anything from quantum computing or quantum machine learning. Okay. I will try my very best from the knowledge, whatever I have from that. Okay. If there is any problems which I am not able to answer, in that case, what I will promise, I will find out and I can get back to you on that. Okay, right? Yeah. Thank you for the thumbs up. And yeah, one more thing is I have already shared, I think, the lecture notes to organizers, I think Parvatam ma'am earlier. So, including today's topic, quantum error correction, I will share the material. Okay, so you can extract from them the organizers and go through it, and you can understand if there is trouble. Anyway, the recording is available on the YouTube. You can go through that. Okay, and go through several times if you want. Again, if you have some problem, you can note down my number, phone number. Okay, let me give my phone number here: 8970994766. Okay, in the chat I have given my number. Okay, and also my email ID I will give. Let me give that. You can write to me or reach to me for anything related. Okay, so yeah,
Sir,
yes, ma'am. Yes.
sir, which area in quantum computing research is going on nowadays, sir?
Oh, very good question, madam. Thank you for asking. Okay, so there are the right now. See, always, if there is a new technology coming up, okay, always people would ask, what is there for us from it? Because we are happy with the existing machine learning and classical computing and everything. Why do I need to go there? So immediate people would ask, what is the application? What is the advantage? So even though the quantum computing and quantum technology is capable of offering applications in wide varieties of directions, remember that in all the existing technology, whatever technology you have, in every place this can be put in. But as of now, immediate application or immediate fruits people are seeing is in two areas. Number one is security. Okay, quantum key distribution or quantum key cryptography. Why? Because if you are able to send the information using quantum cryptography, even the person with a quantum computer itself cannot tap that information and retrieve the information or steal the information. Okay, that much secure it is using quantum key distribution. Number one. Number two application is medical application, which is showing a serious amount of promise. Why? Because the imaging a certain tissue using something called quantum magnetometers. Okay, using NV centered diamonds, people are able to image, like find out the very tiny things in the tissue inside the human tissue. That way people are able to do something called malignant tissue, malignant part of a cancerous. Okay, very early stage detection is possible because it even detects of minute changes in the tissue because of it's a change in the magnetic field. Okay, so that is the another research direction people can pick up because it is an immediate advantage or immediate application coming up in these two areas: security and imaging. Even then, the same area of medical application, there is a machine learning we can use. We can come up with studying the protein folding, and knowing the protein folding, you can design the drugs. Okay, drug design. So that is a very important thing. People are coming up these days. Okay, in the application. Okay, so you can pick up these two directions: medical applications, whether it is imaging or whether it is a machine learning optimization task. You can go for a medical application, or if you are more into, let's say, communication, you can go for secured communication using quantum cryptography. These are the immediate research directions seeing the fruits of quantum computing. Okay, right? So any other things may be extension of machine learning protocols for any optimization like a weather prediction you can study. Okay, or financial case, financial tech, you can predict the stock market, how stock market may do. So these are the other applications. So compared to existing machine learning, you can improve the accuracy, you can improve the prediction accuracy, and you can reduce the error in prediction. Okay, so that is what the other later stages of applications people are seeing. Okay, right? Okay, so I see a good question coming up here. Okay, so I think Ambika ji has asked a question. What is the role of Hermit polynomial in quantum? Okay, Hermit's polynomial in quantum. Okay, I'm sorry, I don't work in this direction, but if you ask a little bit more in elaborative manner, I can answer that question. So I know I have come across the Hermit polynomials in the mathematics and applied mathematics, but I have not seen this is being used in quantum computing. As far as my knowledge goes, maybe it is there. I'm not saying it is not there. It is there. But if you can ask me an elaborated question in connection to the quantum computing, I can answer that. Okay, or I can find out later. Okay, let me go to the another question. Jignaji is asking, how about quantum and blockchain technology? Yeah, very good question. Yeah, yeah. So existing blockchain technology, yeah, people are using, adding a quantum cryptography for that. They can enhance the existing blockchain technology capability to a much more advanced level. Yes, it is possible. That is a very good research direction to explore. It's a combination of classical and quantum cryptography. Okay. Yeah. Any other questions? Thank you. Thank you very much. I hope no background noise with my voice. I will check later the YouTube. Okay. So yeah, it's time now. I think I will just once more. I appreciate all the participants for tuning up on the weekend on the Saturday. I accept that this is your personal time, but because of the workshop or the FTP, people are here. Thank you once again for that, patiently listening to me, asking some intriguing questions. And like say Hermit polynomial, I would find out what is this, and probably if Ambika ji comes back to me on this, we can have a discussion on this. Okay, right? Okay, so with that,
Aswath
thanking
sir,
you all the participants. Yeah, ma'am. Yeah. Ambika,
sir,
please.
this is Ambika.
Yeah, please.
Hello.
Yeah.
Could you able to hear my voice, sir?
Yes.
Sir, I am attending your quantum sensing in MNIT Jaipur. Is it
Uh-huh.
possible to clear after that course regarding the Hermit polynomial?
Yeah. We
Because
can do that. Yeah. Yeah.
okay, sir.
Yeah, you were saying something. Continue.
That's why I called now, sir. There is no issue because I'm keep on listening your class from Quantum 1 to 7 from MNIT Jaipur. So I have seen your name in the pamphlet. I never think about anything else. I just joined because I know well how you are teaching. I really have pleasure to join your class. Keep on want to
Thank you.
continue. Thank you, sir.
Uh-huh.
I will hope to expect you will later on give some basic ideas about Hermit polynomial.
Yes, ma'am. We can do that. Yeah, we can discuss. Yeah.
Okay, sir. Thank you very much.
Yeah. Ma'am, do one thing, ma'am. Just drop an email to me with this
It's
question.
okay, sir. I will because
Yeah.
I'm doing research in that area, but I don't know how it will work out on quantum.
Okay, ma'am. Your background
Okay.
is mathematics, is that mathematics
No,
or which
sir. I
side?
am belongs to electronics and communication engineering.
Okay, I'll find out where the quantum, in which area of quantum this can come. I'll just find out. Okay.
Okay, sir. Okay, sir. Thank you, sir.
Thank you.
Thank you very
Please
much.
drop an email, ma'am. Yeah.
Okay,
Thank you.
sir. Cheers.
Yeah. So, okay. So, see, nice collaborations are building up. This is a good thing to have. So, I urge to the other participants and colleagues to please continue the good work, your motivation, passion in the field of quantum computing, and lot of different uh, background faculty and the industrialists are there coming up and joining the FTPs. Okay, so yeah, I congratulate the organizers and Partham ma'am and other team members of ours. Okay, it's a beautiful set of talks were arranged and resource persons were invited. Thank you, ma'am, for inviting me into such a elite group, and I am very much pleased and delighted, indeed, very pleased and happy to have given these three sessions. Okay, so in future, I would be very happy to see in person and give one-to-one talk or in-person talks instead of having online talks. That would be much more productive in comparison to the ones. So, nevertheless, there is a start we have done. So let's continue and look forward to future to have in person and see you all in person somewhere. Okay. So, Paratam madam, once again, humble gratitude I would like to express to you. Thank you, and uh, see you sometime in the future. And I'll hand it over the session to you. You can take over. Thank you very much.
Sure, sir. Thank you so much. On behalf of all the participants, thank you so much for your valuable presentation today. Your deep expertise and clear explanations on complex topics like error syndrome detection, quantum noises, and quantum encoding circuits were incredibly insightful, and how you made these challenges concept accessible and engaging. Your contributions over the past few days have significantly enriched our understanding, and we are grateful for the knowledge you've shared. Thank you, sir, and thanks to all the participants for your active participation and cooperation. Have a nice day. Thank you.
Yeah, everyone. Bye bye. Have a nice day. Have a nice weekend.